Okay, next up is Aris Chrysakis. He is a final year PhD student, is about to finish very soon. And he will tell us everything about continual learning.
Well,
there
not
is
everything.
To know. Not everything?
Not everything.
Okay, but a lot.
Thanks, Florian. Today I will talk to you about how neural networks can learn new concepts one after the other. We humans are very good at it, but with machine learning models, it's quite tricky. So let's start by introducing the concept of continual learning. And to do that, I will try to contrast it with how machine learning takes place in a more traditional setting. So in such a traditional setting, the first thing to do is collect data. And once we are done collecting the data, we can feed it to the model. We assume that the data set will not change during the training process. And therefore, we can say that the distribution of the data is going to be stationary throughout training. In contrast, in continual learning, the data is observed incrementally throughout the training process. And the data distribution is non-stationary. And what that means is that the average example that we expect to see at each moment in time changes over time. And the goal here is to accumulate knowledge over time. So when we observe a new concept, we want to learn this new concept, but we also want to keep remembering concepts we learned in the past. One naive approach to solve continual learning would be every time we observe new data to retrain the model from scratch. But this approach is intractable, especially when we will observe new data many times throughout the training process. Finally, there might be some other restrictions that may apply in the learning paradigm, such as limited storage or limited computational budget. Here is a very simple machine learning example. So we want to train a model to recognize images of 4 different fruits, apples, oranges, bananas, and kiwis. We collect a bunch of images, we feed it to the model, we train the model, and hopefully at the end it will be able to make useful predictions in unseen examples of these fruits. Now in continual learning, the process would be different. So we would have a stream of data, and in the beginning, one example would be that in the beginning the model would observe only images of apples. Later it would observe images of oranges, then bananas, and finally kiwis. And at the end of the training, we would like the model to be able to recognize all 4 fruits and not just the last one it has seen. Some applications of continual learning, some practical applications. One would be on updating recommender systems, such as those that are used in Netflix or in Amazon for recommending new products to users. And this problem is continual because we constantly have new users signing up to these platforms, and we also have new products that are introduced gradually over time. Then we have large language models which might be pre-trained on next token prediction, and then we would like to take this such a pre-trained model and teach it to learn new tasks one after the other. And by such tasks could be named entity recognition or text summarization or anything else. Then we might have an application in healthcare where we have a model that takes a vector of biomarkers and tries to predict the probability of a certain disease. And such a model could be trained incrementally on new diseases when new data arrives or when a new disease is being identified by scientists. And finally, another application would be to forecast the stock market in the future, given current its current status, and also external information can be also given to the model. Okay, the main obstacle in continual learning is a phenomenon called catastrophic forgetting. And what happens here is that the model, instead of integrating the new information that it observes into its current knowledge, it overrides its current knowledge with the new information. So at the end of the day, it is only able to exploit the current state of the data distribution. And this, in other words, can be viewed as an inability to accumulate knowledge, which is what we want in continual learning. And essentially solving this problem is the main objective here. In my research, I mostly focus on what is called online continual learning, and here we assume that we have a stream of observations which arrive in very small mini batches, which can be even one observation at a time, or 5 or 10. And for each new batch of observations that the model observes, we assume that a fixed number of training steps takes place, and this number is typically very small. It can be anywhere from 1 to 5 to 10 training steps. The main paradigm into solving online continual learning is an approach called experience replay. And in this approach, we maintain a very small memory of past observations. And by very small, I mean it can be like 1% or 2% of the total number of observations in the past of the model. And anytime we observe a new data of observations, we combine it with the same number of observations sampled from the memory, and we perform one training step with this combined mini batch. Here is an example. We assume that in the past the model has seen images of apples, oranges, bananas, and a few examples of kiwis, and at the moment it only observes kiwis from the stream. And here, if let's assume that we receive 5 new observations of images of kiwis from the stream, we would sample the same amount, so 5 images from the memory uniformly at random, and we would combine them. We would combine the 5 plus 5 into a mini batch of 10, and we would feed them to a model to perform one training step. So now let's move on to some of our contributions. Let's start by discussing how the memory population takes place in online continual learning. So the best known approach to perform memory population here is an algorithm called reservoir sampling. And this algorithm, essentially we can prove that at each moment in time maintains a representative subset of past observations in the memory. And by representative, I mean that the subset is IID. So essentially, if we think about all, like at a certain moment in time, if we think about all the observations that the model has seen so far, in the memory there's going to be an IID subset of those observations. So in illustration, if we have, let's say, a stream of 20,000 observations of the 4 fruits that we saw earlier, and there is 5,000 observations in each class, then after we perform continual learning with reservoir sampling as the memory population algorithm, and if we assume that the memory is of size 1,000, then the distribution of the memory at the end could look something like this, where we see that it's the same distribution pretty much between the stream and the memory, and we have 250 examples on average for each class in the memory. And one question here is if reservoir sampling is always the approach we should take in online continual learning. And we argue that the answer is no, especially in the case of imbalanced streams. And what do we mean by imbalanced is when some classes in the stream contain more observations than others. Here, for example, we can see that the number of observations in the stream for the class orange is 9 times more than the class apple. And if we use reservoir sampling in such an imbalanced stream, the imbalances from the stream are going to carry over to the memory. And for example, the class apple is going to be very underrepresented in the memory throughout the learning process, which is going to hurt the training of the model. And to solve this problem, we introduced a memory population algorithm called class balancing reservoir sampling. You can see the algorithm here. It's a bit complicated, but yeah, let me start by saying that this algorithm doesn't make any assumptions about having prior knowledge of the stream. So, it doesn't assume to know how many classes are going to appear throughout the stream, or which classes are underrepresented, how many instances are going to be in each class, or in which order the classes are going to be presented to the model. And there are two main points that we should focus on here to understand what the algorithm does. The first is here, and essentially we try to identify at each moment in time which classes are overrepresented in the memory, and when we detect that the class is underrepresented in the memory, we try to overwrite the instances of the overrepresented classes with instances of the underrepresented classes, so that there is a better balance between the two in the memory at each moment in time. And second, we perform essentially reservoir sampling at the class level in order to not maintain an IID subset of all the past observations, but to maintain an IID subset of each class at each moment in time. And yeah, let's see an illustration now about how the class balancing reservoir sampling approach that we propose compares to reservoir sampling. And on the left, we can see yeah, the memory distribution after the model has been trained on the imbalanced stream if the memory population algorithm is reservoir sampling. And here we can see what this distribution would be if we had used class balancing reservoir sampling instead. And we can see that yeah, the use of the algorithm we propose mitigates the imbalances between the different classes. Now let's move on to a different contribution. We will start by observing that when using experience replay to train a continual learning model, this learning paradigm introduces prediction bias to the model. And what do we mean by prediction bias? Let's assume that we train a model again on the 4 fruits that we saw earlier. And let's assume that we have finished the training and we want to evaluate the model on a set of unseen data. Here we have 4,000 observations, which are equally distributed among the 4 different classes. And a model with prediction bias, the distribution of its predictions would look something like this. So in particular, in experience replay, the prediction bias tends to be towards the final class that the model has seen. And here, because the kiwi was the final class, we see that the model is overconfident that more fruits belong to the category of kiwi compared to the others, even though the testing set that we use here of unseen data is balanced. To understand why this happens, we need to revisit experience replay and how it works. And I told you earlier that when we receive a number of observations from the stream, we combine this number with the same number of observations sampled from the memory. So here, if we were to observe 10 images of kiwis from the stream, we would also sample 10 images of the other fruits in the memory and combine them into a mini batch of 20 and feed them to the model for a training step. What this experience replay paradigm implicitly assumes is that the present state of the stream is equally important to everything that the model has seen in the past, because we use the same number of observations currently from the stream and the same number of past observations from the memory. So, yeah, because we have this implicit assumption that the present is equally important to all the observations that we have encountered in the past, this leads the model to have prediction biases with respect to the most recent class it has observed. And yeah, we did some preliminary experiments to better understand this prediction bias phenomenon, and this is the bottom line of our experiments. And we saw already that experience replay tends to cause the model to be more biased with respect to the most recent class it has observed. But if we shift our approach and put a little bit more emphasis on the memory, we get a reduction in prediction bias. But what we get is more overfitting. And why do we get more overfitting? Because the memory is very small with respect to the entire stream, so it's easier for the model to overfit on the data in the memory. On the other hand, experience replay tends to give less overfitting because the training process is more focused on the past, on the present, excuse me. So the model tends to overfit less on the examples of the memory. And our question here would be, can we try to somehow combine the benefits of the two approaches while mitigating their downsides? And to do that, we start by considering how a neural network is structured. And we split it into two components. We will say that the final layer of the network is the classifier layer, and all the layers that come before that is the feature extractor. So here we have a network of a number of layers, and the final layer is the classifier, and all the layers that come before comprise the feature extractor. And we need to think now, what are the characteristics of these two sub-modules? The feature extractor is composed of many different nonlinear layers, so it has high learning capacity, but because it has a high learning capacity, it's more vulnerable to overfitting. On the other hand, the classifier is only one layer, typically an affine transform, so it has lower learning capacity, but that makes it also more resistant to overfitting. So, given this information, we proposed an approach to train the feature extractor and the classifier of the model in two different steps in order to lower the prediction bias and also not increase overfitting. So on the left, the first training step trains the feature extractor exactly as in experience replay, and in order to do that, we use a surrogate classifier to do the experience replay, because we need to have a layer where predictions come out so that we can use backpropagation to train the feature extractor. So yeah, here we use both stream data and memory data to train the feature extractor. And on the right, we train the classifier layer on a different training step, and here the classifier layer is trained only with memory data. And we do use the feature extractor to compute latent representations in order to get predictions for the classifier, but we do not update the feature extractor in this training step. So here on the right, the feature extractor is frozen, and only the classifier is training, and only with memory data. And because we do this in two different steps, we get both the less overfitting that we get from experience replay and the less prediction bias that we would get if we were to train only with memory data, train our model only with memory data. So here is a recap of the bullet points of this online bias correction approach that we proposed. We use experience replay for the feature extractor. In order to reduce overfitting, we use only memory data to train the classifier in order to mitigate the prediction bias of the neural network. And this approach essentially tries to combine the benefits of both experience replay and training only with memory data. And it results, it lowers the prediction bias of the model in comparison to vanilla experience replay. And it also results in higher learning accuracy at the end of the continual learning process. Here are the two publications from the two works that I discussed. The first one was published in ICML, and the second one was published in ICLR. And yeah, I will be happy to answer any questions. Thank you. Yeah?
So how do you define the test set distribution? Because you said that the distribution of your data evolves over time.
Mm-hmm.
So in some settings, it's the distribution at the end that you would expect to be representative of the things you see in the future.
Yes.
But you seem to be assuming that it's the cumulative distribution over the whole span that is your test set distribution.
So this is a bit application specific, I think, but like in our experiments, we either evaluate at the end and we use a test set that is unseen during the training process, and that the test set has the same distribution as the entire stream that we see. If you would like to have a more continual evaluation, so throughout the training process, I think that, we also have some experiments in this continual evaluation, and there we would need to also update our evaluation set throughout the training process. So every time a new class is seen, we would need to add some unseen data in the evaluation set so that it takes into account the new class. Does that answer the question?
Yeah, I think so. I mean, but it's just kind of I agree. So where you frame the problem, it could be the bias towards the most recent distribution is actually a good thing. And you're assuming it's a bad thing.
But it depends on, if we want to accumulate knowledge, so both retain old knowledge and update our knowledge with the new observations, then I don't know if it's such a good thing, because it's sort of an overshooting problem, right? But if it's more important to adapt to the current state of the stream, because we can think that past observations might be outdated or something like that, then it would be a good thing, I agree. Yeah?
Have you tried your methods on a regression problem also? And if so, how would you do reservoir sampling?
On regression, no, we haven't. But reservoir sampling would work on regression problems because it doesn't need to have the output to work. But our approach needs to have the class label to work. So on regression problems, we might need to do some kind of clustering of the output space and assign pseudo labels to each observations in order to be able to perform the class balancing cluster balancing effect. Yeah?
I was wondering, so in the experience with this setting, you seem to come to the conclusion that the classes in the memory should be equally distributed.
Mm-hmm.
I can imagine that for some classes, more examples, some classes might be more difficult to model.
Mm-hmm.
And you might need more examples than for others.
Mm-hmm.
So I was wondering whether that you consider that problem.
Yeah, so in the paper, in the appendix, if I remember correctly, we have a setting where we assume that we know beforehand sort of difficulty or importance weights for each of the classes, and we show how to expand the algorithm in order to take those into account. If you don't know them, if you don't know these importance weights, you have to estimate them somehow. But if you can do that, then you can use this expanded version of the algorithm to do this online.
Okay.
Yeah.
Maybe one more question. The performance between taking data set stream-wise.
Sorry, I didn't catch.
I was wondering what's the performance difference of your methods, say taking a data set, feeding it stream-wise and doing continual learning, or doing static learning with a complete data set?
It depends a lot on on the how fair you are with the computations, with the computational budget. So and also it depends a lot on the data set, because you have like some data sets where the convergence of the model takes place very quickly, and then you would see comparable performance between offline training and continual learning if you have a large enough memory. And there are other data sets where convergence takes place much more slowly, and there it also depends on the size of the memory a lot. If you have smaller memories, you would get lower accuracies compared to offline training, because in offline training you have all the data at all times, right?
Okay, we still have a lot of time if there are any more questions. Otherwise, I can start with a question. I was wondering how these techniques can be used in large language models. Initially, you said that would be a good application area, but there we're dealing with unlabeled data, right? And I think your research mostly assumes that we know the classes. So could you maybe tell us how this is usually solved?
Yeah, so I think the second paper that I discussed does not really assume any class knowledge in order for the online bias correction to work. The first paper does assume class label knowledge, so it essentially is a supervised learning problem. But if we didn't have, if we had unsupervised data, then it would be, I think, difficult to detect imbalances, because how do you do that? But if you were able to do that somehow by using pseudo labels, then you can use the pseudo labels to balance your memory. And also you have another problem in language data, which is that the data points are not of the same size, right? You might have a sentence that is very, very long and another sentence that is only one word, right? Only a few tokens. So you would have somehow to account for that as well in the memory calculation.
And when you do online bias correction, does it matter how large the feature extractor is in comparison to the classifier? Because that also plays a role in large language models, if that is a factor.
Well, the classifier is always one layer, so the feature extractor will always be much, much larger than the classifier. In my experiments, I have not seen I tried different models of different sizes, and I didn't see any differences in the effectiveness of the approach. So it was equally effective for all models.
Okay. Are there any more questions? Yeah.
Just a quick question. So if instead of retraining the classifier, what if you just took the bias term and reset it to the known distribution?
By bias term, you mean the bias vector of the affine transform?
Yeah, the bias term and the affine transform.
Okay.
You just reset it to the class probability
Uh-huh.
of your target distribution, and you don't change anything else.
Yeah. So I've looked a bit into that because I was also very curious, and it's not the bias term has an effect on the prediction bias, but it's not only that, but the model turns to even the weight matrix of the affine transform tends to be like the rows that correspond to different classes. They tend to be scaled with respect to the prediction bias, and also the clusters of in the latent space that the feature extractor creates, they tend to be of different size depending on whether the class is the present class that we see in the stream, or if it was a class that was observed. So it's more complicated than that, and unfortunately.
Then let's thank Ares again.
Thank you.